All right, so the last section that we need to cover for Physics 1 is about more complex circuits. So we just spent some time talking about series and parallel circuits and how we measure voltage and current. And series just means that there's one path. Parallel means that there's branches. Complex circuits are combinations of series and parallel qualities. Now, there are a couple other sections in Chapter 23, but those are actually reserved for AP Physics 2. It's going to get into the concept of capacitors and how we analyze capacitors and RC circuits. That is not covered in the scope and sequence of AP Physics 1. So we're going to talk about complex circuits, and then we will be done. So, more complex circuits. We can have combinations of resistors that can often be reduced to a single equivalent resistance due to a step-by-step application of the series and parallel rules. So what happens? What does that mean? If I have my battery here and I have this series of circuits or this series of resistors, okay, so that's a basic series circuit. But now what happens if I add a parallel branch? Or if I have another parallel branch with a series component to it. So this would be a complex circuit. And the concept is that we can reduce this circuit to one single equivalent resistance circuit, which means we go from the super complex circuit to a single resistor circuit. And that is a equivalent circuit, meaning that the battery is going to push out some current, and in this case the battery is going to push out the same current, so essentially it does not know the difference. So we're going to learn a little bit on how we do that to analyze complex circuits. So there's a couple problem solving strategies. We draw the circuit diagram and we label everything that we know and don't know. Then we use Kirchhoff's laws and the laws or rules for series and parallel resistors. We're going to do that and one step by step, right? So we might have to draw several of them. We're going to reduce the circuit to get down to eventually one resistor in that circuit. So we're going to make it easier and easier, and then we're going to work our way backwards by determining the current and the potential difference across the equivalent resistors, and then work our way backwards to rebuild the circuit using our Kirchhoff's loop law, Kirchhoff's junction law, and the concept of current to analyze our circuit backwards. Kind of confusing, but we'll do an example. Hopefully that'll help you out. So here's an example. We have these two 10 ohm resistors that are in parallel branches, and then there's this 5 ohm resistor that's in this series. And if I want to know what the potential difference or the voltage drop is across the 5 ohm and each of the 10 ohm resistors, that's really hard to do because this is a complex circuit. So I know a couple of things. I know the current comes out. I know that I can use Ohm's law. First off, let's go in the corner here and I say I know that V equals IR. And I have all of the resistances. So if I know the current that is going through each of the resistors, I can get the voltage drop. The problem is I don't know the current, and I can't simply add my 5 ohm and my 10 ohms resistors together because there's this 10 ohm and 10 ohm branch. So what I'm going to do is I need to also know what, not only do I need to know what the current is, I need to know the current that goes through each branch. Okay? So there's several unknowns, and really it's all about the current because I have the resistors. So what I'm going to do is I'm going to draw another circuit, and I'm going to draw another circuit, and I'm going to keep drawing them until I get down to one resistor using the concept of equivalent resistance. And the way that I do this is I start with the most complex part of the circuit, and the most complex part of the circuit is going to be this parallel branch, right? It's a parallel branch. If I could get rid of that, I'd have a resistor. So I'm going to do what's called an equivalent resistor. If I could replace those two 10 ohms with an equivalent resistor, then I have that equivalent resistor and a 5 ohm in series. Then I can use my series rule and get rid of it. So here's what I'm going to do. I'm going to draw another circuit. There's my battery. And instead of two 10 ohm resistors, I'm going to draw one equivalent resistance, and then I still have my 5 ohm resistor. And my question is, what type of resistor would I need to take these two 10 ohms and replace it with one resistor so that the battery doesn't know the difference? Well, my equivalent resistance in parallel is 1 over R1, which is 1 over 10 ohms, plus 1 over R2, which is 1 over 10 ohms, to the inverse 1 power. 1 over 10 plus 1 over 10 is 2 over 10, or 1/5. The inverse of that equivalent resistance would be a 5 ohm resistor. A shortcut to kind of help you out, if you ever have two resistors in parallel that are identical, the equivalent resistance is just going to be half of whatever that value is. That only works if there's two in parallel that are identical. If there's three in parallel that are identical, it's going to be a third. But if they're not identical, you can't use any shortcut. You got to use a formula. Okay, so then so this is my circuit 1, this is my circuit 2, and now my third circuit is my simplest circuit. And I take these two 5 ohm resistors, and my equivalent resistance in series is just the sum of those two, which means that it's going to be 10 ohms. So now I can start with circuit 3 and work my way backwards. This is 10 volts. To get my current, again, V equals IR, so I is V over R. So right now this 10 volts is being dropped across this 10 ohms, and that gives me a current of 1 amp. Well, if I work my way backwards, the current doesn't change. It's still 1 amp. So that means that 1 amp times 5 ohms, this gets 5 volts, and this resistor gets 5 volts as well. So I can work my way backwards again. And I'm going to go back to circuit 1. This 5 ohm didn't change. The 5 ohm resistor right here doesn't change. It's still 5 volts. Now, the rules with parallel are that each branch gets the voltage drop. So this 10 ohm resistor gets 5 volts, and this 10 ohm resistor gets 5 volts. And some of you might, again, think that this violates Kirchhoff's loop law. No, it doesn't. Watch my laser. I got 10 volts minus 5. Minus 5 is 0 volts. Or I could do 10 volts minus 5 is 0 volts. So that's how I analyze these complex circuits. Now, what about the current going through each of the branches? Well, 10 ohms divided by 5 volts is 0.5 amps. And likewise right here, 10 ohms or 5 volts divided by 10 ohms, 0.5 amps, which makes sense because Kirchhoff's junction law states that I have 1 amp of current leaving the battery that splits, and the sum of the current before has to equal the sum of the current after. So I got 0.5 and 0.5, and that makes 1 amp. You might have done that intuitively, being that, well, if it's equal resistances, they're going to each get half the current. So that's how we analyze these complex circuits. We draw these equivalent resistance circuits, which make it easier and easier, and then we work our way backwards with the information that we can learn from that equivalent resistance circuit. So it takes some practice because it is kind of a weird concept, but we'll get some practice with that coming up. So here again is a picture of what I did. I drew the original circuit, okay? That original circuit had my 5 ohm, my 10 ohm, and my other 10 ohm. And I simplified that. I got rid of the parallel branch to make a 5 ohm circuit, or a 5 ohm resistor and the other 5 ohm resistor in series. And then I made my simplest circuit, so I got my 10 ohm resistor. And then from there, I used that current equals V over R, and I got the current coming out. And as soon as I had that current coming out, I knew it's the same here and it's the same here. Once I had the current throughout, I could say that the voltage drop is the current times the resistance. So I went ahead and said 5 ohms times 1 amp is 5 volts. 5 ohms times 1 amp is 5 volts. And then I knew that because parallel circuits each get the voltage drop, I knew that each branch got 5 volts. Each branch got 5 volts. And I could again use that I equals V over R to get the current through each of the branches. Okay? So it was you simplify the circuit and then you work your way backwards to analyze it. All right, so here's one last example problem. This is a complex circuit, right? I start coming in, and it's a nice little series. But from that, after this, it branches. So there's a series part of it here, or it goes into parallel. And then it branches again. It goes into parallel or series, and then it's got a little series. So the question is, what is the most complex part of the circuit? And the most complex part of the circuit is the fact that there's this 5 ohm resistor and this 10 ohm resistor that are in series with all this other stuff. So you start at the most complex part. So instead of having a 10 ohm and a 5 ohm, what if I replace that with using the concept that resistors in series add together? So instead of having this guy and this guy, I'm going to make a parallel branch that is also 15 ohms. Okay, now what's my most complex part? Well, I got a 15 ohm and another 15 ohm in parallel. So I'm going to get rid of my new equivalent resistance and this resistance, and I'm going to make it, well, I got two 15 ohms in parallel, 7.5 ohms. And that is 1 over R1 plus 1 over R2. Now what's my most complex? Well, I have a 2.5 ohm and a 7 ohm resistor in series, right? So I can get rid of those two and make instead a 10 ohm resistor. And then I have a 10 ohm and a 10 ohm in parallel, so I can replace those two and make a 5 ohm resistor. And then I have a 5 ohm and a 5 ohm in series. That means that's going to be 10 ohms. So that means I could replace this whole complex circuit with one 10 ohm resistor, and the circuit would not know the difference. So here's a partner problem that I used to do. We're not actually going to go through it, but this is a complex circuit, right? If I look through here, I got my two batteries and I got this resistor in series. Well, then I would want to replace these two resistors with one resistor in series. Then I go and I have another battery, so I got to think about how Kirchhoff's loop law works with this. And then I got R4. That's fine if this is in series and this is in series, and I'm replacing these two parallels with series. And then I have R5, which is a parallel of R6 and R7, which is a parallel of R8 and R9. So the first thing I would do is I would combine 6 and 7 into a series circuit, and then I would use the equivalent resistance of 1 over, that's R5, plus 1 over REQ, which is 6 and 7, right? And then 1 over R8 and 1 over R9, and take the inverse of that, right? So I get rid of all of these and I turn it into one series. Then R10 is in series. I got another battery, so that's Kirchhoff's loop law. R11 is in series, and then I would take the equivalent of these three parallel, right? So I would just draw it simpler and simpler and simpler and simpler, and then I'd be able to work my way backwards to analyze the whole circuit. We're not actually going to do this partner problem, but it's a good example of how to analyze a complex circuit. This would be what you would have to fill out for all of them. We're not going to do that. So here's a very helpful tutorial. This guy goes through and he solves a complex circuit from start to finish. I think the video is something like 20 some minutes long. He picked a really complex circuit, right? And he really walks through everything. So if you want to see another example, feel free to check it out. But all we're doing is we're using the concept of equivalent resistance, either being in parallel of 1 over R1 plus 1 over R2 plus plus 1 over Rn. Oops, that's supposed to be an N. To the inverse power. Or in series, where Req equals R1 plus R2 plus plus Rn. And then we're using the concept of Ohm's law. V equals IR, I equals V over R, or R equals V over I, which we typically don't need to use. But we're using those concepts to analyze every single resistor, and we're using the concepts of Kirchhoff's junction law and like what happens to voltage in series and parallel. So that's it. It is complex. It is complex. I'll be honest with you, the most difficult thing that you would ever expect to see on an AP exam, can you see that? Probably not. Let's go yellow again. Nope, that's not good either. Let's just get a new page. All right, the most difficult kind of circuit that you would ever see on an AP exam probably wouldn't be any harder than that. Maybe that, right? So we're not going to get super complex circuits on the AP exam, but we do have that ability to solve as complex as we can based on using the things that we know and understand about series and parallel circuits and how the voltage works and how the current works and using Kirchhoff's loop law and Kirchhoff's junction law. So the very last thing we're going to do, and believe it or not, this is the very last thing we're going to do in AP Physics 1, is we're going to do a lab. And this lab is called Kirchhoff's Gambit. And Kirchhoff's Gambit, all you got to do is print out a puzzle, cut it out, and put it together. And use the rules and the laws of series and parallel circuits and Kirchhoff's loop law and Kirchhoff's junction law to help you determine what or how the puzzle goes together. So we'll be taking a look at that in the next segment. And then we are done with AP Physics 1.